this video, we want to talk about the economic damages from emissions. We're going to use greenhouse gas emissions as our example for climate change, but this can be generalized to kind of all pollution or emissions control. And so on one side we have what are those damages, and the flip side of that coin is those would be the benefits of avoiding emissions or reducing emissions. And then the other side there is, okay, well, what is the cost of reducing or cleaning up emissions or mitigating emissions? And we use the term abatement. And so what are the abatement costs, right, associated with those activities? And just like most things in economics, we're going to be talking about things at the margin. So we'll end up talking about marginal damages and marginal abatement costs. So this graph, I guess the most important part of this graph is this shape. It's kind of upward sloping damage function, and on the horizontal axis we have kind of temperature changes relative to pre-industrial levels, right? So increase in temperature relative to 1990 or pre-industrial levels. And then on the horizontal axis, this is for the United States, you can see that the science article cited is a reduction in GDP, okay, so domestic gross domestic product for the United States in about 80 years. And of course, the bigger the temperature increase, the bigger the damage, or the larger the loss in GDP in the United States. And we can see some estimates here. A 2-degree increase has a decrease in gross domestic product in the United States, maybe around 1%, 1.25%, let's say, of GDP, and things get more extreme as the Earth gets warmer. This graph, same study, kind of just segments where these damages are come from. And the largest fraction, that again I'm colorblind with that bluish or purplish area, is mortality, deaths, and kind of typically use what's called the value of a statistical life. We won't get into too much detail in this class on that, but those are kind of how we're valuing those increased instances of mortality as the temperature increases as we move from left to right on that horizontal axis. And then you can see the other kind of categories. Agriculture looms large, there's some crime in there, labor costs, and coastal erosion, and all kinds of other things. This is just some information from an article that was written by William Nordhaus, who won the Nobel Prize in Economics for his work, his lifetime or career work on climate change issues and governance of the climate problem. And what I highlighted here is the statement of full analysis, right? And the analysis we're talking about is how to figure out what are those damages from emissions, or what are the benefits going to be from emissions control. The full analysis would reflect that economic activity drives emissions. We understand that, right? The emissions isn't the end goal. It's activity that produces the negative externality of emissions. This affects atmospheric concentrations. Okay, that's the science part of this. Thence, climate and the hydrological cycle, which in turn affect human and natural systems, which ultimately contribute to the determination of climate policies. And these integrated assessment models, or this acronym IAM, these models are largely what William Nordhaus won the Nobel Prize for. These kind of really complex and mathematical and computerized models that try to estimate how changes, kind of shocks to the system through increases in greenhouse gases, are going to affect all different sectors in not just the United States, but globally. And so these are very important for cost-benefit analysis surrounding climate change. These analyses have been part of the IPCC reports, the Intergovernmental Panel on Climate Change. These analyses show up in all kind of important policy discussions on what to do about climate change. And so they're not perfect. They don't capture every sector in every way that's going to be affected by climate change, but they are continuously updated, and hopefully they're getting better over time. But these are really what we use to combine everything we know about how human activity leads to emissions and how those emissions impact our environment, and then how that change in the environment is going to impact economic activity. So this graph in particular is looking at mortality associated with greenhouse gas emissions in a warming climate. And the way that this graph works is that kind of fix an emissions projection out. And I think this is kind of a high emissions projection. And then so the horizontal axis is just time. And as you can see, as time goes on, we have an increase in mortality associated with greenhouse gas emissions. And the interesting part of this graph is that it shows you how nuanced models like these integrated assessment models need to be, because they consider, or we need to consider, things like adaptation. And that adaptation is kind of like, okay, well, what's that gap between these two lines on this graph? Is that the top line is changes in mortality caused by increase in emissions without allowing for adaptation, which could be as very simple as moving if you're on a coastal city or if you're in a small island, developing state, nation, but could also be erosion control. I mean, there are all kinds of ways that people adapt. It could be just even air conditioning in places where air conditioning is not prevalent or it's too expensive. And so you think about different ways that you can adapt to a warming climate. And so that dark line or the black line at the bottom is the increase in mortality, accounting for the fact that humans can adapt to a changing environment. And all this stuff has to be embedded in those integrated assessment models that we use. Just very quickly, this is a graph that's kind of showing some of the estimates in terms of global GDP loss from a warming climate, so that temperature change is on the horizontal axis. The vertical axis is the global GDP. And these are early estimates coming from the model that I'm mentioning from William Nordhaus, which is called the Dynamic Integrated Climate Economy, or DICE model. And then there are other models that are listed there. And it just gives you a sense of, even as early as 2007, how economists were combining all this information and coming up with estimates of global GDP loss for warming of, let's say, 2 to 3 degrees Celsius to average mean temperatures. And these, like I mentioned, these studies are prevalent, they're important, and they motivate policy discussions, especially internationally, when we're talking about what are those damages under Paris, for instance, if we exceed our goal of 1.5 or 2 degrees warming. One more slide here on the damages, and this is in the context of what we call the social cost of carbon. And social cost of carbon is very important. It finds its way into federal regulation by the Environmental Protection Agency. Anything that has a cost of benefit associated with climate change or greenhouse gas emissions is going to use this social cost of carbon. And you can see kind of over time, during the Obama administration, where it was first really implemented in policy, $52 per metric ton. During the Trump administration, it went down to between $1 and $8. And for the most part, that was because, well, it could be a number of things that you can kind of intuit. But one of the things is that the Trump administration was pretty clear that they should be measuring these social costs, but only domestically, only those suffered in the United States. Whereas the $52 measure is a global social cost of carbon, because carbon emissions and greenhouse gas emissions more generally are global pollutants. And the last thing on there, on the right, $190, so more than 3 times that. That is what the current recommendation is to the Environmental Protection Agency and the Biden administration. There's a paper published in November, I think, of 2022 in Nature, and it kind of goes over where that estimate comes from, why it's so much higher. In short, there are many damages that those early measures in the Obama administration did not capture that we now know exist. And secondly, it has to do with discounting. We'll talk about that in detail in this class, but how much you discount future streams of money is very important in environmental economics and policy, and in climate change in particular. And so, like it mentions here, the social cost of carbon is used in many regulations that exist today. Many states use it to guide their own policies, so not on the federal side. And other countries outside of the United States also implement the same kind of dollar value in the social cost of carbon. So they're also looking, or the global community is looking carefully at this new updated number. All right, now that we have our idea of what these damages are, at least conceptually, right, from emissions and greenhouse gas emissions in particular, let's kind of sketch this out in a model, or graphical model that we're going to use to evaluate policies in this class. We're going to start with marginal damage. So the idea of marginal damage with respect to emissions is going to be our measure, our dollar value, of all combined negative impacts from emissions. All right, so very simply, on the vertical axis we have dollar monetary amount. And on the horizontal axis, for now, we're going to change this immediately, is that this is the ambient concentration of pollution or emissions, right? It's not just what's emitted. What really matters is how much if we're talking about particulate matter, if we're talking about sulfates, whatever we're talking about is how much is there, or water pollution, for instance, it's how much is measured at that source. So not just, there is some absorptive capacity to resources in our planet. And so it's really what's that detectable emissions level. And we know if you've ever had a water test done or something, I mean, there's usually some sort of acceptable range, and that's the ambient concentration that we're talking about. But importantly is that ambient concentration is a function of the emissions, right? And so to simplify our lives, we're going to be talking about emissions directly. Right? And so ambient concentration is ultimately a function of emissions, but this emissions is the kind of thing that we can regulate. Emissions is the kind of thing that is the result of activity. So we look at this general shape of our marginal damage curve, and things could obviously differ depending on the pollutant, but in general, we're going to see this kind of increasing rate. And so it's not typically a linear function, but increasing at an increasing rate. And so it is costly. This is the marginal damage as we increase emissions, but as we increase emissions more and more, it gets steeper and steeper and steeper. This is obviously just a stylized model, but this kind of general shape is transferable in many situations. If this is the marginals, then any area under that is the total damage. And so if we take a point E, kind of underscore there, or whatever, E bar, E lower bar, then at E lower bar emissions, this is the marginal damage. That's the kind of dollar amount at the margin. And under here, this would be the total damage, right? TD. Right? And in particular, this would be the total damage at E lower bar. So let's consider a movement from E1 level of emissions to E2 level of emissions. And so a reduction of, let's say, global emissions. In this area, what do we want to call this area? A. This shaded area A. Let's see if I can make that pop with some pink. Is it pop? Is it popping? It's popping. This area A, right, when we're going from left to right, then these are the damages for more emissions, but when we're going from right to left, then this is the benefit. The avoided damages are the benefit from emissions control. This is very important to keep in mind. When I'm going from left to right, these are damages that we're suffering from more emissions. When we're going from right to left, these are going to be the benefits, right? These areas under the marginal curves are the totals. So A is the benefit from moving from state of the world emissions 1 or superscript 1 to emissions superscript 2. So here I have the same kind of graph, but with two different marginal damage curves or functions. And you can see this one's steeper, which means that for the same level of emissions, this one is much more damaging than this one. And so what could kind of account for that? Well, it could be that we're just talking about different pollutants, different, lead versus sulfur or something. And so something like lead may be a lot more damaging at the margin than sulfur. But what I really kind of want you to think about is depending on the geographical region of interest, right? If it's global, then everything's kind of combined, like climate change as being a global pollutant. But a lot of emissions control and environmental problems are more local, like water pollution or sulfur pollution, like that cause acid rain. That's not a global pollutant. And so what could let's say we're talking about the same level. Let's say we're talking about sulfur emissions and sulfur dioxide emissions, and we have these two kind of curves. What could account for those two different? Well, this could be the damages imposed in an urban area, and this could be the damages the same sulfur dioxide emissions, but to a more rural area. And the reason is just there are just more people suffering those negative externalities. And so if you're trying to think of what changes the marginal damage curve, well, one is, what's that damage per person? How damaging is pollution, but how many people are there? If you have a pollutant and no one's there, at least in these models, right? If there aren't humans that are suffering these costs, then these marginal damage curves are going to get more flat and not as intense. So it's kind of interesting to think about what could shift or what could change the marginal damage